All right. So today's lecture is going to carry on from some of the work we were doing on Friday. So I'll have a Dropbox folder for you guys with today's dates. We're dealing with within subject analyses, so there's a folder called within. And we're going to deal with this DAT3 data again. So I'll open up this R project file to open up a new R Studio session. And I'll open up this DAT3 analysis. So the first little bit of this file hasn't changed since last day. We load in the libraries and some helper functions. We load in the data and take a look at it. And I happen to know that it's in long format. That's why I called it dat long. And you can actually see that it's in long format, whereby each person has several rows of data corresponding to observations made in each of several combinations of several predictors or several variables. So we've got A and B. A has levels A1 and A2. B has levels B1 and B2. We can see if we sort of scroll down, should be 100 people in this experiment. Of course, very typical of psychological research. So we can take a look at the data. So with the fact that it's already in long format, we don't need to do any reformatting. So we can just generate a plot whereby on the x-axis is the condition of A and the y-axis is the value observed, and two different facets for the level of B, and each line is connecting the dots for a given person. And in theory, I could somehow try to, in theory, A line over here corresponds to A line over here, but I didn't work out an aesthetic mapping that would achieve that with this many people. So I'd shown you the other day that when you have this situation where you can compute for each person an intercept and an effect, or an main effect of A and a main effect of B and an interaction, then you can use the within wide. Let me see, is that even in here? Yes, still. So we've got this within wide model that we'd seen and used before for this scenario of wide data, where we represent the data as being a multivariate normal distribution. Let's see. And to get it to the point where we can use this model, we had to do a whole bunch of computations by hand. So we had to go in and do a little dplyr chain grouping by person, and then within each person computing, well, first the intercept, then the main effect of A, the main effect of B, and then the interaction between A and B. And that's a bit of a pain in the ass, particularly if you had even longer or even more complex design in your data. Now, there are some ways to make this easier, but it would be nice to have something so that Stan figures out these measures. We can just give it the dat long, and it automatically figures out these measures. That would be nice because we're lazy, but it's also nice because when we get into missing data later today, it'll be evident why that's particularly nice. All right, so we're not even going to use this bit of data. I'm just going to delete it. I wanted it there to show you from the other day.
But you were putting that in a wide format so that Stan could handle it?
I was computing the coefficients for each person, or not the coefficients, but the actual, like the intercept and the.
How come you labeled it like that wide
and because it once it I'll even run it and show. Once we run this through, it's suddenly wide data, one person per row. So there's this person's intercept, this person's A, this person's B, this person's AB.
Your four important numbers.
Yeah, exactly. And again, these four numbers simply are a recoding of the original four numbers for that person. But we've had to do that recoding by hand, and that's annoying. So I'll maybe just comment this section out because when I put this up in the Dropbox, I want it to be there. All right, so instead of doing that and then immediately giving the resulting dat-wide as data to the stan file, or the stan model we had where it was within wide, we're going to do something different. We're going to use our get contrast matrix function that came with the helper files, or that helper, the helpers.r file. We're going to say, okay, look in the dat long, and here's the formula for the model we want to express. So there's a main effect of A, a main effect of B, and an interaction between the two. This is the exact same sort of syntax that you should be familiar with from the between subjects use of get contrast matrix. So when we run that, it will show the contrast matrix, because I put a view that line there, and it'll say for each row in the data set, and there were 400 rows in the data set, it'll say what the sort of, it will give the contrast values for each contrast that we need for the to express that model. And that's the exact same as before. We just have, instead of one person per row here, like we had in the between subject scenario, multiple of these rows correspond to a single person. So the first 4 rows correspond to the contrast associated with the first person. Second set of rows correspond to the contrast with the second person, etc. So having created that contrast matrix, we can then submit the data to this new thing you haven't seen yet within long.stan. So before showing you what within long.stan is, I'll show you what we're passing as data. So we have to tell stan how many subjects there are in the data set. We can get that by saying, okay, give me the list of unique IDs in this column. Well, there's a column called ID in dat long. We want the unique values, and then we just want to count the number of unique values. So that's what that length unique dat long ID is. We need to tell it how many observations we have in the data. So that's just the number of rows. We need to tell it how many predictors we have in our model for the data. So that's the number of columns in X. We express that we want an intercept, main effect of A, main effect of B, and an interaction. So we should have 1, 2, 3, 4 columns in, 1, 2, 3, 4 columns in X. So we can just say and call X. We need to tell it what the actual sort of outcomes are. So we give it the column that contains those values. We give it what the predictor matrix is, X. And we also have to give it a list of indices for the subjects. So I've created a sort of helper function that will actually go and look at this column, so the ID column, and it will get out the indices that the code wants. So what do I mean by that? If we actually just run that, there's again 100 people, and what this get subjects indices does is it says, okay, the first person, this row corresponds to the first person. The first person's data starts on row 1, ends on row 4. This person's data starts on row 5, ends on row 8, etc. Now that I'm looking at it, I just came up with an even better idea on how to do this, but I'm not going to go into it, I guess. But I might even simplify this further and show you later. But for now, you actually have to compute in R what the sort of start and stop index in Y is for each person. And this also assumes that you've got your data in a format where it's not all mixed up, where you get like the first person, a given person's data is all in one sequence. So if you had like it shuffled so that you have a data point from person 1, a data point from person 2, and then a data point from person 1 again, or if it were ordered by any other column but the ID column first, this would break. So I should maybe even make note of that at some point. I'm going to add some code here to make sure that I'll do it. You'd want to do it before you generate the contrasts. So make sure that the data is, and I'll make this wider, sorted by ID. So we'd say dat long equals, we could use the, let's see, arrange. I guess, yeah, let's do it. Wow. The old style way of doing things, not using dplyr, is to say dat long equals dat long, and you say order dat long ID. That's the old way of doing it. I guess I'll show the new way of doing it. It would be dat long equals arrange. I guess let's do a pipe. And you'd say ID. So it's up to you which way you do it. That should have the same consequence each time. I happen to know that dat long was sorted by ID in the first place, and we didn't really do any modifications of it. If you've produced your data from a series of transformations of the raw data, you probably want to make sure that it's being sorted properly by running either of these lines, or both. That would just be redundant. Then run the contrast matrix, and then run the model. So I've told you what the model needs, but I haven't shown you the model yet. So let's bring that open within long.stan, and I will pop it out and pull it over. So the first thing to notice is that there's a whole new section. Instead of starting with data, it's starting with functions. You don't need to know anything about what's going on up here. In the same way that you can define your own custom functions in R, you can define your own custom functions in Stan. When you do it in R, you can do it anywhere in the code. When you do it in Stan, you have to do it at the beginning in a section called functions. So I created this thing called getCoefs that I'll explain in a moment. We've got the data section, again, just enumerating the things that it's expecting as data coming in. So number of subjects, total number of observations, number of predictors, the vector of observations, the predictor matrix, and indices talking about the start and stop indices in Y for each subject. We've had transform data before where we use that to sort of automatically scale the data when we were doing between subjects analyses. And I think within Y did it as well. It did the sort of Z scaling. Here we're going to do that Z scaling, but we're also going to use this getCoefs function. And you can think of this getCoefs function as achieving the same thing as what we had in our R code up here that I just commented out, where it will, here we knew what the model was, that we were going to model it as having an intercept, main effective A, main effective B, and an interaction, and so we specified by hand each of those things. getCoefs takes as input the coefficient matrix, and it just will automatically work out what it needs to compute given that coefficient matrix. You also have to give it the Y values themselves. Here I'm saying giving it the scaled Y values. And, oh, go ahead.
Just a really quick question. You may get to this, but in terms of this, is this sort of like an expandable formula where it doesn't matter whether we have just the two or like that?
Yep, exactly. So by putting this inside Stan, I've also made it so that this is flexible to an arbitrary design.
And we don't have to give it any, like we don't have to label the...
Nope.
Perfect.
Yeah, exactly. I intended to make it fairly idiot-proof. Yeah, exactly. So it will take whatever the design matrix that you specified by your predictor matrix, And the data here, I'm scaling the data as I'm passing it in. So the coefficients will therefore be scaled coefficients that it computes for each person. And you also have to give it those subject indices so they can work out which subject gets which chunk of the vector y.
It's still purely within subject's design.
Yep.
Yeah.
Yep. Still purely within subject design. I haven't.
It won't
No.
guess around that or something.
Sorry?
Like this.
No. This
It won't
isn't
like
smart enough to know whether it's within or between. Here we're still talking about purely within. Wednesday, we'll talk about mixed designs. Okay, so this will yield something called scaled coefs, which will be the exact same thing as if we'd actually gone and by hand figured out what the coefficients were. Now, it says scaled, and that's implying that we actually are scaling in some manner. Here it's scaling by what's in the y column. So again, that's going to mean that all our priors are going to be on the z-scores, which again is a nice scale that we have pretty decent intuitions on, so it's easy to put pretty default priors on. But beyond that initial creation of these coefficients, the model is exactly the same as we had for the within wide. We have a vector for scaled coef means. So for each coefficient in the design matrix, we'll get a mean for that coefficient. So we'll get a mean intercept, and a mean A effect, and a mean B effect, and a mean A by B interaction. We'll get a standard deviation. So how do subjects differ from one another on each of those coefficients? Again, each person gets a coefficient. So a given person gets a intercept, a given person gets an A effect, a given person gets a B effect, and so you can look at how people vary from one to another in the magnitude of those effects. And then finally, a correlation matrix to express that these coefficients might be correlated across subjects. So somebody with a high intercept might have a high B effect. Somebody with a low A effect might have a high A by B interaction effect.
With the intercept as a coefficient as well?
Yep. If you remember over here, when we said view X, there's a column for the intercept. So the model's the exact same as before. You sort of have weakly informed priors, achieved through z-scaling the data, and then you express that each subject's data is sampled from a multivariate normal distribution with this mean vector and this covariance matrix, so where the covariance is simply the combination of the correlation and the standard deviations. And in the generated quantities, I think we had this as well. So where these coef means and coef SDs, these scaled coef means, scaled coef SDs are being expressed on the Z scale. We want to know what the actual, on the scale of the data, what those correspond to. So we've got coef means here, coef SDs. Coef SDs are their scaled counterparts multiplied by the standard deviation of y. And coef means are the scaled counterparts multiplied by the standard deviation of y. And it's only the intercept that needs that mean added back in. So this code kind of assumes, I said that it's flexible for arbitrary designs. Interpreting this coef means afterwards kind of assumes that you've made a design where the first coefficient is the intercept. If you had a model where you didn't have that structure, you just comment out this line, and it would be it would apply.
Wait, sorry, what's the 1 in the brackets?
That's saying that the first element of the coef means vector. Again, there's 4. Well, in the case that we're dealing with, there's 4 columns in the predictor matrix. So there's 4 entries in the coefficient vectors. So the first element in that coefficient vector is the intercept, the coefficient corresponding to the intercept. So in addition to multiplying by the SD, we want to add in the mean of y.
Okay, so these are, I mean, I'm just trying to wrap my mind, like, what the final number of generated quantities, for instance, is just the number of lines of code there, right?
Sorry?
Sorry. So, I mean, we're scaling back to get like the numbers in the same scale as the same
Yeah,
units
yep.
as our code.
Yep.
So like the first thing, first you are outputting coef means the vector.
Mm-hmm.
So that's like going to be.
So this is in, like, I guess what we would call initializing, saying that there will be an object called coef means, and it should have this many slots in it. I guess one thing that I kind of glossed over is that when I say, for example, coef SDs equals scaled coef SDs times SDY, this is a single number. This is a vector of numbers. This computation gets, it's just each element gets multiplied by this single thing. And that returns, again, 4 elements that get assigned to the 4 slots in SDs. Ditto this one, the 4 empty slots in coef means get assigned the result of this, which in turn is 4 things. And this final one, it says, okay, assign into that first slot that is now not empty anymore. Grab the value that's in that slot, add the mean to it, and put it back in. Yeah.
First slot of coef means.
Yeah. Yeah, exactly. Yeah. All right, so have I actually done any changes? No, I didn't. All right, so with that file and the data as I described sort of collected coming in, we can run the analysis. So I will run that, and it should just immediately go because I compiled it earlier. It goes fairly quickly, but I don't know, 10 seconds. I'm impatient, so I would do that one as parallel. So we can use our stand summary function to look at, for example, coef means, passing in the, I guess, the contrast matrix so that we get nicely named output for this. So we can see the intercept and its credible interval, the main effect of A, its credible interval, main effect of B. And these numbers should be precisely what you get out of the version that's wide within wide. We haven't changed anything about like the structure of the model. We just changed sort of where we had to do various computations. So instead of having to do the computations outside in R, we allowed Stan to do the computations before it did its sampling and things. So we can also look at, so this is sort of what the population mean is for each coefficient. We can also look at sort of how people vary from one to another and their sort of manifestation of those coefficients, manifestation of those effects, which is what that SD's one is. And we can look at the degree to which various effects might be correlated in their manifestation across the population. So big giant correlation matrix. We saw this last day. I still have plans to make something inside stand summary recognize that this is a correlation matrix and only return the upper triangle that are the unique values. But you can glance through and see that there's no like incredibly strong correlations in there. And that's consistent with the fact that I made this data up without any strong correlations. But if there were, that would be potential fodder for discussion because there's a whole field of individual differences research where they're interested in things like not only is there on average an effect in the population, but to what degree effects are related to one another in their manifestation.
But when we did the coef means summary, we did find an interaction effect.
Let's take a look. That's different from, so an interaction is different from saying that across the population, the degree to which one effect manifests, like the magnitude of one effect influences the magnitude of the other. So a correlation is talking, sorry, the interaction is talking about within a given person or at the scale of the sort of the population mean, whether being in one condition influences the size of the effect in the other condition. But the correlation speaks to something different. It's about like what's, as you look at how people vary from one to another on these effects, to what degree they are correlated. So they actually are I can see where you're coming from. They sound like they're actually talking about something similar, but they actually are like can be considered as completely separate things. But I would say of fairly equivalent interest.
So what's the term for the second one? Just the correlation of.
Yeah, you talk about the
variance?
correlation matrix. You talk about individual differences, whether there's. I mean, another way of putting it is to say knowing. So if there were a correlation between somebody's magnitude of the A effect and their magnitude of the B effect, say it's a positive correlation, you could say knowing somebody's A effect allows you to predict what their B effect is. That people with, if it's a positive one, you could say people with large A effects also have large B effects. But that doesn't mean that within that person or across the population that there's an interaction between A and B. It's a different thing, because the interaction between A and B is saying that as you look at the conditions that reflect the combination of A1, A2, B1, B2, that's the influence of that the level of one variable influences the magnitude of the effect at the other variable.
Yeah, makes sense. Right.
Yeah.
So that's good.
Okay. I still included the code here I mean, it's going to be the exact same thing as we saw last time, where you can compute and visualize the posterior for each condition. Again, you use the get condition post now, give it the object with the posterior samples, you tell it what parameter you want, and what the design matrix was, or predictor matrix was. That creates something called CP that contains, it just works out from the design matrix and the coefficients what the predictions at each sample is for the conditions that generated this design matrix. And you can then pipe that through to summarize and ggplot and create a pretty plot like this. Again, this helps double check like if you get effects, which condition is bigger than the other condition, what the sign of the effect actually means for the relative ordering of your conditions. It can also be nice to show in people just want to see plots of some sort, but be wary of interpreting, say, the credible intervals on the seeming overlap of credible intervals at the level of the conditions, because the final word is on things like whether there's a main effect of this, main effect of that, or an interaction, is the samples from the coefficients that are in, this table is the final word on things. So.
Just to be clear, that table is saying there is an effect of both and an interaction effect.
Well.
It's not a great interaction, but wait, no, it is overlapping 0 completely.
Yeah. So 0 is pretty thoroughly included here, and you can kind of visually see it. Like these are pretty parallel.
Just 50% on the left.
Yeah. I do this so that you could just copy and then say this is the mean interaction effect, and then parentheses this. So fairly straightforward. This is still the same model fundamentally as the within wide, where we pre-computed all the coefficients, but this one will be just a little bit easier to deal with in terms of we don't have to work out what the coefficients are ahead of time. It does it all by itself. Okay, which brings us to missing data. So I'm going to bring up my camera, do a little drawing first. So in theory, let's just imagine a super simple scenario of paired data where you've got height on one axis and weight on the other axis, and you've got a whole bunch of samples from a bunch of people. And we could express a model for this data that should be relatively familiar, whereby we say there's a sort of normal distribution of weights with some mean, I'll call it mean W, and some variability, I'll call that SW. And we can similarly imagine part of this model is that there's some normal distribution of heights with some mean H and some variability SH. And then finally, some sort of something that represents the idea that there seems to be a relationship between height and weight, and that's just the correlation parameter. So correlation between height and weight. So we've got 1, 2, 3, 4, 5, a 5-parameter model for this data. Now, what if I were to say, I've got a new data point coming in. I've lost its weight or its height measurement, but I do know its weight measurement. So I know that it has a weight right here. I can't place it in the vertical at all. I could maybe sort of convey that it's there by having a line. I can't place it in the vertical at all, but I can place it in the horizontal. Typically, if you were using any of the tools that they might have taught you during the undergrad, you'd take that data point and realize, oh, I can't actually, like SPSS won't handle this. Well, I'm not going to say that because I haven't used SPSS in like a decade. I mean, a naive approach would be to take the assumption that you can't use that data point since it's incomplete data and toss that person. This can become troublesome when you've got sort of an increasing proportion of missingness in your data, in which case you end up tossing a lot of people, and that sort of will diminish your power relative to other approaches. So what other approaches are there? Well, some people do things to try to guess what this person's data for height could have been, and they sort of take a multi-step process. They fit the data they fit a model to the data without that person, and so they have the height and weight, or without that person and any other people that have incomplete data. And so they'll get an estimate for the mean weight, the standard deviation of weight, the mean height, the standard deviation of height, and the correlation. And then they'll use that model to express, okay, given a person with this weight, what's the most likely height for that person? So that gives them you can actually see how that would, sort of visually, you can kind of see, it would be pretty, given this sort of seeming visual organization of the data, you probably would be rather suspicious of a prediction that the person's height's way up here. You'd probably be pretty suspicious when it's down here, but you probably think that a point sort of in the center of this ellipse, as this line cuts through the ellipse, would be sort of probably the best point. And that's functionally what that imputation approach achieves, is it sort of looks where this ellipse is and finds where the line cuts the ellipse, and the sort of midpoint or the maximum point of that ellipse it uses as the sort of imputed value for that person. Then you'll see people actually rerun the analysis with the imputed values in there. That seems like your, I don't know, it seems a little inelegant that you're doing these analysis 2 times. Does it mean that you're kind of double dipping in that sense? Or I'm a little wary of that. Certainly, it's the case that in sort of the Bayesian framework, you can do both the imputation part and the analysis all at once in a manner that allows the data that you do have for each person to help inform and increase your power of the analysis, while also then also getting sort of some guesses for what people should have responded or likely responded given everybody else's data. So what parameters? So I've got no height information for this person. What parameters can they inform me about? Like, can they influence the estimation of?
Just the 2 with weight only.
Yeah, exactly. So if I've got a weight measurement for this person, they can influence the estimation of the variability of weights and the estimation of the mean of weights. They won't be able to give us much in terms of estimating the correlation, and certainly nothing about the height and the variability of heights and the mean of heights. Ditto, somebody with a height but a missing weight, so maybe we have sort of a height of somebody right there. That person can help and certainly inform these 2 parameters, not so much this, and definitely not the height, the weight parameters. So the way we will treat this scenario of missing data is to still give the model all the data, but tell it which data points have missing data. So we could say that there's a weight for this person, but we don't know what the height is. And what the model is going to do is it's going to treat that person's height as a variable, as a parameter in the model. In the same way that we are sort of doing sort of a inference on what are the most credible values for the mean and what are the most credible values for the standard deviation, we're also going to do inference now on what are the most credible values for a given person's missing data point. So let's take a look at how that's achieved. And I'm going to skip to, so in this model, we maybe would have, if we just had data like this where it's height and weights, we would have just taken the data and used the within wide. I'm going to skip to the more common models that we'll be using where it's like condition 1, condition 2, and we're actually interested in the difference between conditions. So I'll actually draw that. Okay, so we've got, I guess, A1 and A2, and usually we actually have really strong correlation in our research because we're dealing with effects with very wide between subjects variability relative to very sort of smaller within subjects magnitude of effects. So that causes a scenario where a model, it's best to think of the model in terms of an intercept and effect. But if somebody's missing data for, say, A2, so they only have a data point for A1, maybe I'll put it out there. They only have a data point for A1. You can't compute an intercept for that person, and you can't compute an effect for that person. So certainly the prior use of within wide, where we outside of stand computed the intercept for each person and the A effect for each person, isn't going to work because we don't have an estimate for that person's A2 to generate those coefficients. What we're going to do then, if you open up within long missing, I'll make it, pop it out, pull it over. This within long missing starts again with the functions section. It's got a section of data that up up to here is the exact same as within long. The extra stuff for within long missing is these three things. You have to tell it how many data points are missing. You give it the indices in Y of the data points that are missing. So if the third entry in Y is missing, there'd be a 3 in this list. If the fourth entry in Y is also missing, there'd be, it'd say 3, 4, etc. So it's a list of numbers as long as there are a number of missing data points corresponding to the entry number in Y that is missing.
That's also like kind of sent in through some code in R.
Yeah, so I'll show you how to compute that in R. Compute these things in R. The other thing it wants is like the inverse of this. So it wants the indices of the missing data. I also need you to give it the indices of the present data. Given those, we've got a transform data section. And notice we're not doing, all we're doing in this transform data section is we compute the mean of Y and the standard deviation of Y. And we compute a scaled version of Y. But critically, when we are doing this again, this is just the standard Z transform that we've done in the past, but we're defining the mean of Y only with respect to those values that are present. Ditto, we're defining the SD of Y only with respect to those values that are present. We're still scaling all of them, so even the absent data points are getting scaled. Now, I'll show you what we're actually going to be doing is whenever there's an absent data point, we'll just put a 0 there anyway. So it's a 0 that gets scaled, but it ignores it. So you might think, how is an NA going to get scaled? You don't need to worry about that. The critical thing is that all the indices of all the Y's that are present are getting scaled using only the present data to define the scaling parameters, so the mean and the standard deviation. Is that clear?
Yeah, the only thing that's strange is like you're still using the absent points as like a number of the total, but I guess that's not going into the mean or anything.
Nope.
So like
nope.
It's just kind of there.
Yeah. Yeah, we still have the same number of entries in scaled Y. So, parameter section, the same as earlier, up to here. So we've got the coefficients, the coefficient means, the scaled coefficient means, the scaled coefficient standard deviations, correlation matrix. But now we've got this new thing, imputed for missing. This is a vector of the same length as the number of missing items. And this is what I mean that we're going to treat missing data points as parameters. If there were just one missing data point, there would be a vector of length 1, and there would be just a single thing that we are going to do inference on to say what are sort of credible values for this thing.
And there could be two different types, like if you could be missing like A1 or A2 data, but they're combined and you like.
Yeah, so because we've scaled the data, we won't need to worry about the idea that we might want to distinguish between missing A1 or missing A2. They're going to be given this parameter vector is going to be given a default prior that's centered on 0, standard deviation of 1. So since all the data will have, or since the scale data will have a prior that's centered, the data actually is centered on 0 and standard deviation of 1 by scaling it. That will mean that they don't need labels for which condition corresponding to the missing data. Question over here?
Just to clarify, earlier when we were talking about the height and weight thing, you said, for example, if you had just the weight, we would form like the mean and the standard deviation of the weight and not the height. Will doing this, does doing this at all affect the mean or the standard deviation or anything of the other value that you're missing? Like, just because I'm does it actually put something in for that value, or does it just skip over it when it's computing?
It will actually literally be putting something in for that value, and be making guesses for what that value should have been.
Okay, so
And-
it can affect the data, but
Yeah.
because we're using our like priors and all that, any effect it should have should be sort of within the realm of what you would normally expect.
Yeah, it's only going to make guesses for what should be put in that are consistent with what the rest of the data and data from other people are like. So yeah, they're guesses, they're educated guesses, and yeah, they're not sort of.
Okay. And now one more question. I apologize. We may get to this eventually, but are you eventually going to talk about what to do, for example, if we have like repeated measures, but we're missing data from a given time point?
Well, that's what this is. Like, imagine
Okay.
like somebody was measured at time 1, but they dropped out. You don't have them for time 2. You still want their data. Their data has information in it, and any information helps your inference. So
Well, I wasn't sure if it would be possible to like actually use their data for time point 1, but completely say ignore their data for time point 2.
you could do that, but
So without having to like affect perhaps the actual data that you do have. I mean, say you had 100 participants and 50 of them dropped out. I mean, that's inferring the data from 50 participants at time point 2 is quite. I don't know if that's.
So the degree to which, so obviously having all the data from everybody is going to be ideal, and your inferences will be most accurate under that circumstances. As you get an increasing proportion of data missingness, you will have, well, increasing imprecision in your inference. No bias any which way, just you're going to be less certain at the end. But including that data under certain constraints, which I'll mention in a moment, is always better than just not having it at all. So, and that's what this is going to automatically do, is it will sort of be able to extract what information it can from it, and not only give you guesses for that person, what should have been there for that person, but also just improve your overall confidence in your inferences at the end, so smaller credible intervals. Now, I said there, as long as certain conditions are met, this assumes that missingness is a random phenomena, that there's no, people with high scores at time 1 drop out because they don't need to come back, like it was a study session or something. That would be a missing not at random, in which case you'd want to develop a more complicated model, which we're not going to deal with today. You guys could maybe make a note and email me to deal with it down the line if you think that you have missingness not at random in your data.
Okay. That's something that personally would apply to me, but
yeah.
I don't want to derail this entirely. So.
Yeah.
I'm still a little bit confused philosophically though. For like, so say the height and weight example, and you want to make an argument in the end that like there's this strength of correlation between height and weight. You've got some like weights here that don't have height correlates. I don't see like how that's gonna help you in any way to make that argument. It's gonna make it like clearer and narrower your confidence interval.
Yeah, well, by this estimate of the correlation between the height and weight is influenced by particularly this estimate of the variability in things.
Okay, so I guess
so it does, your ability to talk about the correlation is estimated by or is influenced by the information that this point can give you for this. So let me give you an extreme case. If you had, let me plot. How would I? So, and then a couple data points that are sort of kind of high leverage in terms of driving like a correlation, and a bunch of missing data that's all within here, then these are pretty anomalous. They won't be sort of the way the Bayesian data analysis works out is that having these data make these data points less sort of influential.
Yeah.
However, if you actually did have missing data for data points out here, then these ones would remain influential, and therefore that's going to affect the row that you, or the correlation that you're estimating.
Yeah, I guess
across
the thing is, like, in theory, all those weights exist in the sample, so you could just like add them in anywhere. But this is saying like, okay, no, the sample, there's more people at a certain weight, so you just happen to get those through your random sampling.
So like even in just the univariate case where you're just talking about like observations along just a line,
it's a little low.
the fact, there we go. The fact that there are other observations out in the extreme influence like the degree to which the other observations nearby are like believed by the model. Just the way the math works out. If you happen to like add some data out near this one's presence is going to pull out the SD. If I add more data that's closer in, that's going to pull in the SD. If I add a couple data points that are further out, that will make this one frankly more believable. It's going to pull the SD out. So insofar as these points are extreme sort of in both dimensions, having some missing data that is out consistent with them will actually influence the correlation parameter as well.
That makes sense.
Yeah. All right. So we've got the idea that we've got bringing in the data as in the raw format. We scale those data points that are there relative to the mean of those data points that are there and the standard deviation of those data points that are there. We have our expression of the standard multivariate parameters where there's a mean coefficient vector and the standard deviation coefficient vector and a correlation matrix. And then this new thing where it's a vector of values that are going to be guesses for each missing data point. So the first one might be a guess for a missing A1. The second one might be a guess for a missing B2, etc. So they're all sort of mixed in here. Now we're going to use the have I shown you transform parameters as a section yet? I don't think I have. So transform parameters is a section where you can, what we're going to be doing is creating this thing called scaled coefs, which previously was just data. We used the get coefs to take in the data in long format and reformat to wide format with coefficients. Now we're creating this in the transformed parameters section. We're also creating this thing scaled y with imputed. And all this is going to be is a combination of these guesses plus the scaled y. Or, well, better to phrase it, it's a combination of the scaled y where the missing data has been replaced with these guesses. So scaled y with imputed is going to be of length of the original data set. The first thing we do with it occurs here.
Are the guesses coming in as single values or as ranges of values?
The guesses are coming in as single values for each sort of iteration of how the model works. This is kind of getting into the nuts and bolts that I've been trying to hide from you guys, that what actually happens when Stan takes in this model and is doing its computation, it's evaluating the transform parameters. So it evaluates the transform data section once to generate the things that you've expressed in there. Usually these are things that are a function of the data. So this scaled y is a transform of the y that we give it. It then sort of initializes some parameters. And as it's searching through the parameter space, it runs all the computations that you define in the transform parameters and model section for each sort of point in the parameter space that it explores.
So could you say they're running in single values with like different values according to
Yeah,
the iteration?
every iteration
Based on,
it's getting a different guess.
And like the frequency is probably based on like how confident you are.
Yeah, exactly. Yeah. So we've got this thing scaled y with imputed, and it's just going to combine the present values with the imputed values. So we are saying the scaled y imputed, and specifically those entries in this. So it starts out as empty, and we say those entries corresponding to indices in y that actually are present, put in the scaled y's corresponding to indices of y that are present. So all this does is for every entry in y that's present, we fill scaled y with imputed with the scaled version of that y value. Now, more interestingly, for every entry in scaled y with imputed where there was a missing value in y, we give it the vector, we give it a guess. So if there was only one missing data point, this would be a vector of 1 long, so the single entry in y that's missing would get that thing. If there were 2 missing data points, by indexing by the indices of missing, say it was the 3rd and 5th data point that were missing, this vector is 2 items long, but this expression would say, okay, replace the 3rd and 5th, replace the 3rd with the first entry in here, replace the 5th with the 2nd entry in here. So it automatically sort of slots the guesses into their appropriate spot. Critically, the first entry in this will always correspond to the first missing thing. Second entry in this will always correspond to the second missing thing, in which case we can take a look in the posterior, what are the credible values for a given person's missing data point. That might be of use for scenarios where you're not only doing sort of exploratory research, but you want to sort of label people as having certain disorders and things, and yeah, we'll actually get out predictions for their missing data point. So having now created this new thing scaled with y imputed, we can now compute this other thing I promised we were going to compute, which is the scaled coefficients. And again, this scaled coefficients is going to act just like before when we didn't have missing data. So we want to use the getCoefs function. We're giving it the predictor matrix, the contrast matrix here. Instead of giving it the original data coming in, we're giving it this scaled y with imputed. And as before, giving it the subject indices. So this will get out coefficients for each person given their real data plus any data we had to make guesses at. And it will give us a set of coefficients for that person, their intercept, their main effective A, main effective B, interaction, or whatever the experimental design is. Having created that scaled coefs, we can then have the model exactly as we had before, where you've got some priors on the mean vector, the standard deviation vector, a correlation matrix, and each person is modeled as having a coefficient vector, a scaled coefficient vector that's a multivariate normal as a function of those things. Now the one added line in here is expressing that this vector of imputed values is distributed as normal, mean of 0, standard deviation 1, which again is a fairly weakly informed prior, given that we've standardized the existing data, the y's, to have a mean of 0 and a standard deviation of 1.
Would you expect that to change at all if you had like fewer versus more missing values?
No.
Because like the standard deviation in theory might get bigger with fewer values. I would just randomly guess, but maybe not.
The standard deviation actually is fairly unbiased. It's only when you get down to like only 2 or 3 observed values in your it actually gets bigger. Like in theory, it gets bigger as the standard deviation gets bigger as you add more data, but it's a fairly weak effect. So yeah, if you really wanted to guard against that, you could put like 2 there. So it will still give us back though. This section is identical as before. I didn't think of it, but if you wanted to actually look at the scaled y with imputed, so if you're actually interested in a given person's prediction for a missing value, you'd need to undo the scaling, which I didn't do down here. But if you're interested in that, that can be a fun exercise for you to figure out. It should be pretty straightforward from how we do it with these ones. So is that pretty straightforward? We've gone from a model where you had no missing data, and therefore in the transform data, we could use the get coefs function to immediately create something that's called scaled coefs. But when you have missing data, you need to express those missing data points are things that you're uncertain about, that you want to do inference on. Once you have sort of guesses for those things, then you can create this thing called scale coefs, which is, again, the wide coefficients for a given person.
Not sure. Maybe it's not convenient to do this, but would it be possible to see an example like with the previous A1, B1, A2, B2 data where you have like half of it is just straight up missing versus half of it is like half missing?
Yeah, that's what we're about to do. Yeah, so over in our code, in the stat3 analysis, we've got a section, induce data missingness and analyze. So we'll set a seed for reproducibility, so you all get the same results. I arbitrarily chose 10% missingness.
And that means the 10% of the subjects are missing their data completely? Or
This is going to be 10% of the cells are missing data. So this section is like what would happen behind the scenes. Sorry, I guess. Yeah, this section is like what's happening behind the scenes. You don't sort of really need to understand what's going on too much, except to trust me that I'm just going to. This will ensure that precisely 10% is missing. So if I run this and we view dat long now, we see an NA there, NA there, NA there. So there's some NAs for people now. It's about 10%. If we have data in that format, and let me actually, so I don't have to read it again, dat long back equals dat long. Nope, that doesn't work because I've already modified the data. So I might as well not put that there. So I'll run it first and show you that it works. And then I'll run it again, eliminating anybody with any missing data. And that might be only 10%. Might be lower, I guess. 10% is the maximum. So if a given person has less than, or more than 2 missing data points, that means somebody else doesn't. Okay. So given this data, let's say we didn't see this bit of code. All we see now is this dat long that has missing data. We can use this within long missing to do the data analysis. We have to do some computations ahead of time, so we have to count how many is missing. So you can use the is.na function. So it's the value column that we're interested in. You can use the is.na function to ask, is it NA or not? And the sum of that will yield the number missing. So n missing is going to be 40, which is precisely 10% of the total. And we can, again, use the is.na, but now instead of doing sum, we'll do which, and that will give us the indices of the missing. And we can say which are not missing. Use the exclamation mark to invert. So is.na is going to yield a vector of trues and falses. trues where there's an NA and false where there's not. So to get the indices of present, we take that index, that vector of trues and falses, and we invert it using the exclamation. So that gives us the indices of present. And one quirk of Stan is that it's not going to let you keep NAs in where there are NAs. So you need to put a number there. It can be anything. 0 is fine. 999. It actually functionally doesn't have any consequence whatsoever if what number you put in there. So I'll just put 0. Having...
So I was going to say, actually, that would also be beneficial if, for whatever reason, your program spits out a 0 instead of an NA for...
Yeah. You'd want to convert those numbers to NAs first so that you can use these lines to compute the number missing and the indices, etc., and then give it just an arbitrary.
It won't actually replace it anyways, right?
Sorry?
Otherwise, it won't use the...
If you use read underscore CSV, you can tell it what the NA value is. So if you don't have any NAs, but you get 999 wherever there should be an NA, you can tell it that. So yeah, you'd want to do all that ahead of time so that by the time you get to this, there's only NAs or real numbers. Okay, so we have to replace any of those NAs with just a number. Doesn't matter what that number is. And that's what this line does, at which point we're ready to run the model. The data coming in is the exact same as before, except we're adding these 3 entries and missing, indices of missing, and indices of present. Oh, we missed something. I'll show you. I've got it over here, ready. Okay, while that's going, and notice it's actually running a little more slowly now. That's because it actually needs to do that computation on every iteration rather than once at the beginning, that getting out the coefficients. So missing data has some time costs, but it will always have information benefit. Okay, so this printed out right at the very top. Diagnostic warning non-fatal, left-hand side of the sampling statement may contain a nonlinear transform of a parameter or local variable. If it does, you need to include a target plus statement with the log determined absolute blah, blah, blah. Anyway, it's complaining about this, which we've had in all our models, that scaled coef is distributed as multivariate normal. So what is happening here is it's warning us that we create scaled coefs in transform parameters, and then we express that it's distributed as something. And usually you'd have to be concerned about that for reasons that are too detailed, but I'll tell you, because this is occurring in the context of us creating something from the use of missing values, you can ignore this warning. So this is like the one time you can ignore this warning, when it's like you've got missing values and data combining in to create this thing called scaled coefs. That triggers this weird warning, but this is the one time that you can ignore this warning. There are other circumstances that trigger that warning that you would be concerned about. Here, you don't need to be concerned. Meanwhile, I'll look at the output. It took quite a bit longer, 40 seconds for each chain. I'll double check these counts that they're fairly low, and indeed they are, because I asked for 2,000 iterations, and they're all like less than 100 certainly. So I should be good. So we can look at the summaries, and I mean, it's the same data as before. We've just tossed some, so the results are going to be largely consistent. This interaction still includes 0. Standard deviation, I mean, it's all going to look the same. So.
If we graph, can we see like, but I mean, the effect should have weakened a little bit, right?
Yeah. We should be less certain of some things. It's going to be hard to guess which things, though, because you'll be missing data. Well, I guess it should be.
It's not missing like in a uniform manner. So shouldn't everything just be a little
Yeah, everything should be just a little bit more uncertain.
compared to the previous?
Let's see. How would I achieve that? I think the best way for me to do that is to rerun the previous. But this one should take about 10 seconds. Oh, I should have told it not to refresh, because that's going to scroll it all the way off. All right. Well, okay, let's take a look at this. So that's about 9. No, that's not how that works. 18.
No, it was how it works.
Yeah, it was how it works, yeah. $13. This is for the coef. Wait. Yeah, no, this, I reran this on the original data, but still after replacing a bunch of values with 0. Because I'm looking at these, I'm like, these are really big relative to what we just saw. Okay, so I'm gonna reread in the data.
You just like open the other file or something.
Well, no, because I'm just gonna reread in the data. Contrast matrix is the same though, so I should be able to just run this again. So I'm gonna call this, well, I'll let this run. And I'm gonna meanwhile go back down here. Hopefully I can still scroll back up to when we originally did this. There we go. All right. Copy this. Put it over here. Here. Okay. So the outset, we have separation of about 6 points on that. Compare that to, pretty much the same. Let's see. 96 to 103, pretty much the same. 453, 461, pretty much the same. I mean, 10, 12 to 809. Well, I think it's so close it'd be hard to actually say.
So
Let's.
it's super similar when you do the impute
Yeah.
thing.
Okay. So let's actually now. So I'm gonna retoss. And I'm gonna create a section that create new data consisting of only those subjects with complete data. Okay. So dat long2 equals dat long. So I only want a certain subset of rows. Am I going to do this? I'll do it in dplyr. I need to get myself used to doing dplyr. And so we're going to filter. And we want only those for its ID. If we wanted to create a thing that only consisted of those people that were missing data,
Like finding an A and see what the corresponding ID is, and then like cut those out entirely.
yeah. I'd say that long ID such that actually I'm going to do this out here because it'll be more sensible. So missing data. Oh. So is.na. Make this bigger so I can see. Okay, so that's going to list all those. I'm going to ask for the unique ones. Oh, dat underscore long. Okay, so missing some. Is there no column called? Oh, is.na dat long isn't going to work. All right, so there's like 29, 30, 40, 50, 29, 30, 31, 32, 33, 34, 35. 35 people with some missing data.
That's their ID numbers there?
Those are their ID numbers, yeah. So if I wanted to select just them, I'd say ID in missing some. This in, it's like if ID equals this one, or if ID equals this one, or if ID equals that one. So it's whether the thing on the left-hand side is anywhere in the thing on the right-hand side. It's a logical test. This will come out as true. If the thing on the left-hand side isn't anywhere in the thing on the right-hand side, it comes out as false. So that would select those ones that are missing data. So again, I want to pipe in dat long, and I'll assign it into dat long complete. Okay. View dat long complete. Oops. So we shouldn't see any data missingness in here. All right. So, question? No? Okay. I'm going to go up here and grab the code we used to create X. I'm going to copy this too to make sure it's sorted. And I'll scroll down, put it here. That long complete. So we'll, oh. Okay. That should make sure that view that long complete. It's ordered by person, which it is. We'll get contrast matrix for X. And everywhere I see dat long, I need to put dat long complete here. Okay. That's running. I'm going to go up and copy code for the means. Put that right there. Okay. So again, this is once we've tossed 10% of the data.
Slightly less, because there's like
Yeah.
5 people.
Let's actually, I'm going to start at the very beginning. Again, read in the data. Don't need that. Let's toss a good chunk. Let's do like 30%. Where is that though? Start here. 30%. All right, so that's going to yield this. And this was with everybody. Or no, this was, actually, yeah, this was the result from actually doing data imputation. So 97 to 109, that's wide, no. Yeah, that's wider than this. And this is wider than this. 5.5 to 46 to 55, 41 to 58. So this is wider. This is wider. Oh no, yeah, this is wider. So yeah, yay.
They kind of like jumped around in interesting ways. Like the lower boundary.
Yeah,
both
yeah,
got lower.
it's fairly noisy.
Yeah.
Yeah, okay, so I'm happy I was actually validated in. Yeah. So in general, if you think it's reasonable to assume missing this at random, it's always more statistically powerful you'll always end up with more precise and more accurate inferences if you still include what data is not missing and use this model to do inference on the missing values. Make sense? Mm-hmm. All right. Well, I'm going to cut it off there.